Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. This is the second lecture of the course of Electromagnetic Theory, and in this lecture I am going to solve some problems related to the vector products. Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture I am going to discuss the electric field intensity due to a sheet of charge. So in this case, the charge is distributed uniformly along an infinite sheet, or we can say that the charge is distributed over a surface. So this is a surface charge, and here we will be given the surface charge density, which can be defined as charge per unit area, and it is represented by rho s. So rho s is equal to charge divided by area, and since this is an infinite sheet, so the charge is distributed along my y-axis from minus infinity to plus infinity, and along z-axis from minus infinity to plus infinity. So the area is equal to length into width, but in this case, since the uh, surface is extended from minus infinity to plus infinity for both the axes, so it will be written as length multiplied by length. So we know that charge per unit length is equal to line charge density. So Q over L can be replaced with rho L, and it will become rho L over L. And before deriving the expression for electric field due to a surface charge, we will consider that a line charge is distributed along this differential element. So this is the differential length, and along this length, uh, the charge is distributed in the form of a line charge density, and this entire y-axis is divided into infinite segments, and one segment can be considered as a line because the width of this segment is very small. So the width of this segment is dy, and the surface charge density will be equal to the line charge density divided by dy. So the line charge density will be equal to surface charge density multiplied by dy. Now we already have the expression for the electric field due to line charge, and we will use that expression, and we will integrate y from minus infinity to plus infinity, and then we will get the expression for electric field due to a surface charge. So, but this is most important thing before deriving the expression. In the previous case, when we were deriving the expression for electric field due to line charge, we considered the whole z-axis uh, divided into infinitesimal segments, and one segment was considered as a point charge, and we already had the expression for the electric field due to point charge, and by integrating z from minus infinity to plus infinity, we got the expression for electric field due to line charge. Now we have the expression for electric field due to line charge, and we will divide this entire surface along the y-axis into infinitesimal line segments, and one line segment has the differential width which is approaching to zero, and that infinite segment will be considered as a line. So now we have the expression for the electric field due to line charge. We will use that expression, and then we will integrate that electric field from minus infinity to plus infinity for the y-axis, and after solving that integral, we will get the expression for electric field due to a surface charge. So d rho L is equal to rho S dy, and dE will be equal to rho L over 2 by epsilon rho d rho a rho. So this is the expression that we already have, and for a line charge, okay. So E rho is equal to rho L over 2 by epsilon rho a rho. So this is dE, and it is equal to d rho L divided by 2 by epsilon rho a rho. So when we integrate this expression, then we will get the expression for the electric field due to a surface charge. So d rho L is equal to rho S dy. So here we will have ds rho y divided by 2 pi epsilon, and rho is equal to x square plus y square, because this is the line segment that we are assuming, and this line segment is along the z-axis. So definitely rho vector will be equal to x square plus y square under root. And here we will have x over x square plus y square under root ax plus y over x square plus y square under root ay. So x over x square plus y square under root will be equal to cos theta, and y over y x square plus y square under root will be equal to sine theta. So it will be cos theta ax plus sine theta ay. And this is the assumed angle theta because we are calculating the electric field at this point P, and this point is lying at the x-axis and its components are x 0 0. So this angle is theta, and this is our source. So the source coordinates are 0 y 0, right? Because this is along the y-axis. So when we calculate r, so it will be calculated as x square plus y square under root. So this is the y-axis. So this r is actually base equal to rho vector, and this is the rho vector, and rho is equal to x square plus y square under root. Z component will not be involved in calculating this rho vector because our line charge distribution is along the z-axis. So z component will be absent. So it will be having the components of 0 y, and this has the component of x and 0. So the distance will be x square plus y square under root. So these vectors can be extended more as I have shown in this figure. So if this angle is theta, this angle will also be equal to theta, and this is our ex and this is our e. So e can be transformed into two components. This is ex and this is ey, and ex is equal to e cos theta. And this is our expression for the differential electric field. And again, we will use the symmetry as we used for the line charge. Now our differential source is located at this point, and if our source of line charge is placed at this point, then definitely electric field intensity will be having both the components, y component and the x component. But if we integrate from y minus infinity to plus infinity, it means we have the same charge distribution at minus y plane and the same charge distribution at the plus y plane, plus yz plane. So along the plus y axis and along the minus y axis, we will have the same charge distribution. And due to this reason, there will be only one component of the electric field, and that component will be along the x-axis. So this y component will be equal to 0. So we will ignore this y component, and only this cos theta component will be present. And cos theta is equal to x over x square plus y square under root, and this is dex, and it will be equal to x over x square plus y square. So this is dy. Now we just have to integrate this expression, and this integration is very simple. Ex will be equal to rho sx divided by 2 by epsilon integration from minus infinity to plus infinity dy over x square plus y square. And we know that the integral of x over x square plus y square dy is equal to tangent inverse y over x. So we will just write tangent inverse y over x from minus infinity to plus infinity, and it is rho s over 2 pi epsilon tangent inverse infinity minus tangent inverse minus infinity. Tangent inverse infinity is equal to pi by 2, and minus tangent inverse minus infinity will also be equal to pi by 2. So it will become pi, and at the end we will get rho s over 2 epsilon. So this is the expression for the electric field due to a surface charge. And one thing to understand here is that if we have the surface charge distribution along the yz plane, then the electric field will be directed along the x-axis. If our charge distribution is along the xz plane, then our electric field will be directed along the y-axis and vice versa. So this is the final expression, and we know that for a point charge, E is equal to 1 over 4 by epsilon q over r square. So it will be actually inverse square distance relationship of the electric field. If we have a line charge, electric field will be inversely proportional to the distance. And if we have a surface charge, infinite sheet of charge, then E is independent of the distance. So this is very interesting finding from this derivation. So if we have a bulb, so bulb actually behaves as a point charge light bulb, and the intensity of the light will be reduced by r square as we move away from the source. So this is the same intensity of light reduction as we have observed for the point charge. So if we have a tube light in our rooms, tube light behaves as a line source of light, and in that case intensity of light will be reduced by r. And in the case of electric field due to line charges, it also reduces by a factor of r, inversely proportional, and it is inversely proportional to r if we have a line charge. Similarly, if we have a sheet of charge, or you might have observed in old in new buildings and new shops that there are several tube lights connected like an array, so it becomes a grid. So this type of grid actually behaves as a sheet of light. So this is actually a sheet of sources of light, and this type of source of light actually is a very in attractive, because in if we have such sheets of light at the roof, the intensity of the light will be almost similar as we move away from the source, because in case of sheet of charge, as is the case in electrostatics, if we have a sheet of charge, the intensity of the electric field will be independent of the distance. And here, if we have a sheet of lights, the intensity of the light will be independent of the distance. So that's why tube light actually is a strong source of light, and light gets very small attenuated uh, with the increase of the distance. If we have a bulb in our room, then the intensity of the light will reduce more as we move away from the source. So the same principle applies to the light sources, and the same principle applies to the charge sources. So in charge sources, we will have electric field, and in the sources of light, we will have the intensity of light. But the relationship of the intensity of light or the intensity of the electric field will be same as we move away from the sources. So I hope that interesting point is understandable to you. You can read this discussion by yourself as well, and I think it will be clear to all of you. So now I will solve a very interesting example on surface charge distributions to calculate the electric field at four different points. So after solving this example, it will be quite understandable to you how to calculate electric fields due to surface charges. So in this example, we are given three sources and three sheets of charges. First sheet has 3 nanocoulomb per meter square density at z is equal to minus 4. So this is this surface charge density. Second source of charge is 6 nanocoulomb per meter square, and it is located at z is equal to 1 surface. And the third charge is actually placed at z is equal to 4. So z is equal to 4 is another plane, and the charge density is minus 8 nanocoulomb per meter square. So find the electric field at P1, and the coordinates of P1 are 2, 5, minus 5. So this is point P1, and we have to calculate the electric field intensity at this point due to all the three sheets of charges. And we know that in surface charge distributions, there is no distance dependency. So we just have to use the trivial expression, which is rho s over 2 epsilon. Rho s is given to us, epsilon is a constant, so just we have to put these values in the expression for the three charge densities. There is no uh, involvement of the calculation of the distances. So for the point P1, there are actually total three sheets, and this is our point P1. Now we have to use some common sense before solving this problem. So this is the first surface charge rho s1, and this charge is positive 3 nanocoulomb per meter square. And due to this surface charge, the direction of electric field will be downward at this point P1. At this point, the electric field will be downward. Similarly, due to this sheet of charge, again this is positive, so the electric field will be downward. And due to this sheet of charge, since this is a negative charge, and the electric field lines will be upward at this point. So one thing to remember here is that due to positive charge, electric field actually originates outward from the source, and due to negative charge, electric field is directed towards the source. So electric field lines always originate away from the source in case of positive charge, and electric field lines move towards the source in case of the negative charge. And since this is a positive charge, so the electric field lines will be downward below this sheet and upward above this sheet. Similarly, for this sheet of charge, electric field will be downward below this sheet and upward above this sheet. And this is a negative charge, so electric field lines will be upward below the sheet and downward above the sheet. So at point P1, the electric field will be in the negative z direction due to this first sheet, negative z axis due to the second sheet, and positive z axis due to this third sheet. So we will use minus 3 or 3 nanocoulomb and minus AZ. So this is the rho S1, 3 nanocoulomb per meter square, but we have to use minus AZ unit vector because the electric field lines are downward. Similarly, for this one, again, it will be 6 into minus AZ, and for this, it will be minus 8 into minus AZ. So it will become plus 8. So that is what I have used over here, but here I have just used different symbols for the surface charge densities, and I have used positive sign for the AZ. So for rho S1 I have used minus 3, for rho S2 I have used minus 6, and for rho S3 I have used plus 8. Okay, because the electric field intensity due to this sheet of charge is downward, so it will be minus 3. Again, due to this sheet it will be downward along minus AZ, so I have used minus 6, and it will be positive due to this sheet, so I have used plus 8. So minus 3 minus 6 plus 8 nanocoulomb per meter square divided by 2 epsilon AZ. So the final answer is minus 56.5 AZ. Now my second point is P2, and P2 is actually 4 to minus 3, and since its Z component is minus 3, so it will be lying somewhere here. It will be along at the minus, it will be below the y-axis because z component is negative, but it will be above this sheet because z component for this sheet is minus 4 and the z component of this point is minus 3, so it will be located over here. So this is our point P2, and now at this point the electric field due to this sheet is positive, it will be upward, so it will be used as plus 3. Due to this sheet it will be along negative z axis, so it will be minus 6, and due to this sheet again it will be upward because this is a negative charge, so it will also be positive. So 8, minus 6, and plus 3, these will be the signs which will be used. So 8, minus 6, and plus 3. Rest of the calculation is same, and at the end we will get 283 AC volts per meter. Similarly, the third point lies at minus 1, minus 5, 2. So this point will be lying somewhere here above the second sheet of charge. So at this point, the electric field due to this sheet will be positive. So 3, if due to this sheet, it will also be positive. So it will be used as 6, and due to this sheet, it will also be positive. So it will be plus 8. So I have used 3 plus 6 plus 8 divided by 2 epsilon, and 961 AZ volts per meter is the final answer. Finally, E4 has to be calculated at this point P4, and P4 is actually lying over here, and its Z component is 5, so it will be above the third sheet of charge, and at this point electric field due to this sheet will be upward, due to this sheet it will also be upward, so 6 and 3 will be used as positive, and due to this sheet it will be downward because this is a negative charge, so it will be minus 8. So 3 plus 6 minus 8, and the final answer is calculated to be 56.5 AZ. So only this understanding has to be developed for solving such problems on charge distribution, surface charge distribution. So I hope you have understood the concepts which are discussed in this tutorial. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.